So this is 3-4, systems of linear equations in 3 variables. All right, we're going to be able to solve systems of linear equations in 3 variables, and we're going to also be able to do that with real-world problems. All right, so think back to the beginning of this chapter when we were just working with systems in 2 variables. All right, so the way that we could solve those, we had graphing, we had substitution, we had elimination, and then the fourth thing on that list, if you remember, was matrices. We haven't gotten to those yet, all right, but this time, instead of solving systems like x plus y equals 5 and 2x plus y equals 13, all right, instead of having a system in 2 variables, now we're going to have a system in 3 variables. And when we do that, we're adding a third dimension, all right? So with this system in 2 variables, we only have 3 possible scenarios. We have intersecting, parallel, or coinciding lines, meaning those lines are the same. But when we add a third variable and a third equation, we're adding a third dimension. All right, so we're going to be looking at equations of the form like 2x plus 3y plus 10z equals 15. And when we are looking at an equation like that, this is the equation of a plane instead of a line. All right, and so I kind of hinted at this way of thinking with linear programming in our last section, but today we're really going to dig into it. Okay, so what are our possibilities when we have 3 planes like this? And here's an image that you have access to in your notes, or it's kind of blown up here. So the options are, if we have 3 planes, so a plane is just like a piece of paper, picture it like a piece of paper. Those pieces of papers could intersect in such a way that they have exactly one ordered triple that is their solution. All right. It's also possible that it looks something like this, where there is more of like a line. So those planes intersect at a line. And this is a case where there are infinitely many solutions. Okay. And then there's also all sorts of possibilities where there's no spot that those 3 planes intersect, meaning there would be no solution. So kind of similar idea. We have one solution, infinitely many solutions, or no solutions. But geometrically, they look a little bit different because we are in 3 dimensions. All right. So if a system has exactly one solution of the form x comma y comma z, this is called an ordered triple. It's kind of like we've seen ordered pair. Ordered pairs are x comma y. So an ordered triple is x comma y comma z. So with these systems, even though we can graph, we can substitute, we're going to pretty much want to use elimination with maybe some substitution here and there. All right, we're mostly going to be solving these algebraically because it is difficult to visualize it. I'm going to come back to this visual representation after we've looked at them algebraically. All right, so these 2 systems are going to pop up in our algebraic solutions in just a second, and then we'll look at them in GeoGebra to see what they look like. All right, so example 1, this is on page 10 in your notes packet. We're going to solve by hand. So remember how with eliminating with two variable systems, I said you need to organize your work very carefully. This is why it's important. All right, so let's start off by labeling our 3 equations, A, B, and C. And I want to try to look and see, all right, which variable do I want to eliminate? Which variable to eliminate? And I want to choose a variable that's going to be easy to eliminate in a couple of different ways, all right? So, for example, say I want to eliminate my z's. Notice how I have a 2z right here, and then a z and a positive z and a negative z. Knowing that I have that 2z here, there's going to have to be some sort of multiplication involved in order to get my z's to cancel, okay? Unless I just add my a and my c, that positive z and negative z would cancel out. But in order to get another thing, we have to, another equation, we're going to have to do some multiplication. So the overall picture, we're going to eliminate one variable, and then we're going to get a system in 2 equations. Okay, system with 2 equations. And then we're going to eliminate another variable. We're going to do it again. We're going to eliminate again. All right, right now we have 1, 2, 3. All right, we're going to eliminate one variable that's going to bring us down to a system in 2 variables. And then we're going to eliminate again to get to the point where we just have one equation that's going to be hopefully our solution. All right, so let's take a look at this and say, all right, I'm going to choose my x's because they're all just having coefficients of 1. All right, so what I have to do, I'm going to take my first equation A, and I'm going to say, all right, do I want to add it to B or do I want to add it to C? Do I want to subtract anything? I can see that I have a positive x and a negative x right here. So if I add my a plus my c, that's going to give me x's that are eliminated. All right, so x plus negative x, those cancel. Y plus 2y gives me 3y. Z plus negative z is going to give me 0z, so those are going to cancel out really nicely. And then 2 plus 1 is going to give me 3. So this is actually a really nice situation. My x's and my z's canceled out, meaning that right off the bat, I can tell you that y equals 1. All right? That doesn't always happen, but if it does, it's super nice. All right? So I've eliminated my x's, and then now what I have to do, I can't use a and c again. I have to use either a and b or b and c to eliminate my x's again. All right, so I'm going to eliminate my x's again. All right, and so because I see that b has a positive x and c has a negative x, I'm going to do b plus c. All right, so then x plus negative x, those cancel out. Negative y plus 2y is going to give me y. 2z plus negative z is going to give me z. And then 2 plus 1 is going to give me 3. All right. So I've used A and C, I've used B and C, and I've generated 2 new pieces of information, a couple of new equations. So this is kind of where I would be in that process. Normally, if my z's had not disappeared up here, I would need to keep going. All right, and then eliminate again as if I had a system in 2 variables. This is going to be kind of nice. All right, so I know that y equals 1, and I know that y plus z equals 3. So I can use this piece of information and substitute 1 in for y. All right, and it tells me that z equals 2. So now I know y, I know z. I can back substitute into the original equation. Substitute into the original. And let's see what happens. I'll choose the top one, x plus 1 plus 2 equals 2, meaning x plus 3 equals 2, meaning that x equals negative 1. All right, so I have my x, my y, and my z. To finish this out, I need to write my solution as an ordered triple, x, comma, y, comma, z. So these are our 2 planes that intersect at the point negative 1, 1, 2. Okay, and so let's see what does that look like in GeoGebra. And then this will be the last thing I go through in this video, and I'll start a new video for the next couple of examples. All right, so let's take a look at this. This is a great resource if you haven't played around with it. I'd recommend doing it. It's kind of fun. Might blow your mind a little bit. I'm going to plug in all 3 of my equations, x minus y plus 2z equals 2, and then negative x plus 2y minus z equals 1. All right, and so I start the situation where I have these 3 planes. All right, so if you ever get lost of where you're at with GeoGebra, just go home, click the home button, and this will take you so that your x-axis is the red one right here, your y-axis is the green one going from front to back, and then your z-axis is going up and down. All right, so we have 3 planes, and since our solution was an ordered triple, if we plot this ordered triple, negative 1, comma 1, comma 2, we should see that that point A, is a spot where all 3 of our planes intersect, and that looks to be true. So we know that our solution seems to be correct, right? If your answer was way off, maybe you had a point that was, something like this. See how that point A, that's not even close to any of the planes. It's just kind of floating out in space. That would be an indicator that your solution is probably wrong. All right, so that's an example of a system in 3 variables with exactly 1 solution. Tune into the next video for infinitely many and no solution.